Hey everyone, we're looking at class 7. Let me just get this straightened out here. All right, so hopefully this is close enough. You should have a copy of this though, so it shouldn't be too bad for you. So let's get going real quick. So a soccer player runs 100 meters north, 45 meters west, then 100 meters south. Draw the diagram below. It does not need to be to scale. So I always like to make my little starting dot here. We're going to go 100 meters north, 45 west, and 100 south. What's the distance traveled by the soccer player? That's the total distance traveled. Total length of the path, 245 meters. Displacement, how far you are from where you started. So go from where you started to where you finished. Draw a nice line. Make it dotted, however you want. That's the resultant also. Okay, the vector sum of all these. That's going to be 45 meters west. Okay, resultant. In this case, the resultant is displacement. As I said in the last video, vector and resultant are just math speak. When you add vectors together, the sum is called the resultant. Since we are adding up displacements, distances, the resultant is a displacement. Magnitude is simply the size of the resultant. In this case, 45 should be meters. A car moves along a circular track. The car makes one revolution around the track. If the radius of the track is 40 meters, find the total distance traveled by the car. So if we look here, draw a little picture. There's our radius, 40 meters. The distance traveled, since it goes around once, is the circumference. C equals 2 pi r. Equals 2 pi times 40 meters, 251 meters. What is the displacement of the car? Hint, it stops where it starts. Therefore, the displacement is 0. How far it is from where it started is 0 meters. This is one of the few vectors where there's no direction. All right, so let's check out this question here. It says a person runs 2 kilometers north and 5 kilometers east. Though you certainly don't need to use a scale drawing here, it's good practice to do an easy question this way. You could definitely do this on your own. So let's pick a scale. You can pick an easy scale like 1 kilometer equals 1 centimeter, but that's going to be a little bit small here. So here's what I'm going to pick. I'm going to pick 2 centimeters equals 1 kilometer. That's going to make this a little bit bigger and be a little bit better practice for us. The first thing you should do before you draw is figure out, okay, how big do these need to be? You see this is 2 kilometers here? We have to get that into centimeters on our scale. Now we're not converting to centimeters, okay? We're just converting to like a scale for centimeters. So I'm going to write 2 kilometers times, I want centimeters, I have kilometers. So what I want over what I have, and I get 4 centimeters. Kilometers cancel. So this is going to be 4 centimeters long. Now I have 5 kilometers. Multiply by 2 centimeters per 1 kilometer, and I get 10 centimeters. Kilometers cancel. So now I can draw it. So I kind of made it easy for you. I said start here. So my first vector is going to be 4 centimeters straight north. Label it 4 centimeters, 2 kilometers. My next vector is going to be 5 kilometers east. Don't start here again. You start where that last one just ended. So let's draw that out. 5 kilometers east. That's going to be 10 centimeters long, I think we said. So that's step 3. Connect tail of the first vector to tip of the second. Okay, so that's drawing in the resultant there. And that's also, I can measure that out. I think that's 10.7 centimeters about. I'll call it 11. 11 centimeters. So that new vector we just drew is the resultant. That's the vector sum. The magnitude, the size of the resultant, is 11 centimeters. And that's also the displacement. Well, the displacement has to be in kilometers, so let's convert that. so 11 centimeters. How do I convert? My ratio is 2 centimeters to 1 kilometer. So I want kilometers, so 1 kilometer goes on top, 2 centimeters goes on the bottom, centimeters cancel, and I get 5.5 kilometers. To get the direction, that's usually with respect to the imaginary eastward direction. That's what I like to pick anyway. So I'll go for that angle there. Take my protractor, put the little nub of the protractor, that little circle there, right on that start line, line it up, so that this black line here on your protractor is parallel or right on the east axis. And it looks like it's about 22 degrees. Now, since this is measured with respect to east, see how east is this way? We measured 22 degrees from it. Well, we started east and went north of it 22 degrees. So we're going to say north of east. A little bit strange to think about, but remember, we're measuring from the east axis going north. If I measured this angle right here, as some people did, which is fine, that's east of north. You started at north and measured east of it. Confirm your answer by using the Pythagorean theorem. So you could do 2 squared plus 5 squared, take the square root, and you would get 5.4. Right, if you use the Pythagorean theorem here, 2 squared plus 5 squared, get this, you would get, I believe, 5.4. We got 5.5 kilometers, if you recall. So pretty close, so it checks. So this next one here, you also have to make a scale. So you can choose a scale that's easy, like 10 meters equals 1 centimeter. I'm going to use the scale that 1 centimeter equals 5 meters to make it a little bit bigger. So the student walks 10 miles west, 20 miles north, 70 miles east. Total distance is 100, right? The length of the path. And we made our scale. So 10 meters. How many centimeters is that going to be on my scale? Oh, I can show the math. I'm going to do it right over here. 10 meters times 1 centimeter over 5 meters gives me 2 centimeters. 20 meters is the other one, times 1 centimeter over 5 meters. Meters cancel, is 4 centimeters. And the last, 70 meters times 1 centimeter over 5 meters. Meters cancel, is 14 centimeters. So let's draw it out. So this first one is going to be 2 centimeters west, because that's what 10 meters is. Label as you go along, so this is 10 meters or 2 centimeters. I label it both ways. This next one is 4 centimeters, straight up. So 4 centimeters or 20 meters. And the last is 70 meters. So that's 14 centimeters. It's going to go pretty far over, all the way to here. 14 centimeters, 70 meters. Draw a line from where you started to where you ended. Make sure the arrow points towards where you ended. So it starts where you started, ends where you ended. This is my resultant, which in this case, the resultant represents my total displacement. And that's about, I'm just going to estimate there about 13 centimeters. But to convert that to meters, 13 centimeters times my conversion factor, 5 meters over 1 centimeter, because I want to cancel out centimeters. And I think that comes out to be 65 meters. For direction, measure with respect to the imaginary eastward direction. Put the little nub on the start here spot, the beginning of the resultant. Measure 0, 10, 20, about 22 again. That's just a coincidence. And that's north of east. All right. Just want to check my math real quick, make sure I did this all right. It looks about right. Yeah, it looks pretty good. All right, so let's check out some of these vector ones. You don't need to draw these to scale. These are just really good practice. So a 737 is a type of airplane. So a 737 is traveling east at 200 meters per second. So that's what we're going to do first. Draw that 200 meters per second. A tailwind is blowing 43 meters per second east, the same direction. How do you add them? Add them tip to tail. It doesn't really matter if you put the vector here and point that way or the vector here and point this way, as long as the tip of one is touching the tail of the other. In this case, 43 meters per second. So our velocity then, our resultant, goes from where we started to where we ended, 243 meters per second. East. The next one, B, is a standalone question. Forget about A for a moment. 200 meters per second is still the velocity of the airplane if there were no wind. Now 43 meters per second west. So you start the next vector here and you go back because 43 meters per second points west now. Then you draw a line from where you started to where you ended and you get 157 meters per second east. Okay. Common incorrect way people do this one is they do this. 200 meters per second. And then they go 43. And somehow they come up with 243 meters per second. That is not accurate. Those vectors are not lined up tip to tail. That's tail to tail. No good. All right. So now we're flying north, 300 meters per second. And there's a crosswind going 56 meters per second east. What's the new velocity? So we have to do our Pythagorean theorem. Comes out to be about 305 meters per second, right? Doing 56 squared plus 300 squared equals about 305. That's a little bit estimated. But we still need a direction. So we need this angle here. So I would use theta equals the inverse tangent of opposite 56 over adjacent 300. Could you use sine and cosine? Yes, you could, but those would rely on using this number here. And maybe that's not entirely accurate. That is a little bit rounded. So let's see. I'm getting about 10.6 degrees. That's going to be, so we measured from north, right? So you should always measure with respect to one of the cardinal directions. In this case, it's north. So it looks like it's east of north, because you start at north and go to the east of it. The next question is effectively identical, but the wind is going west instead. So this still ends up being 305 meters per second. This angle here still ends up being 10.6 degrees. Here's the only difference. Starting at north, this is going west of north, right? If this is north and we're measuring angle with respect to north, it's west of it. So it's going to be west of north. So this is partially why this east of north, west of north is really important to differentiate. This one is going northeast, this one is going northwest. Okay? So we're going to practice with these vectors a little bit more and more. This is a really important skill that we're going to use throughout the year. So it's kind of nice to get it out of the way now, just so when we get to it later in the year, it's not new to you. Okay? So let me know if you have any questions in class.